Hey, this is Charlie Thompson, and this is the Lab 4 intro video for temperatures. I'm just going to tell you what the other videos are about, what you'll be doing this week, and hopefully just give you enough information that'll make everything else easier in this lab. So what are we going to talk about this week? We're going to talk about temperature. We're going to talk about temperature scales and conversions, Celsius, Fahrenheit, going back and forth. We'll talk about wind chill, heat index. We'll talk about temperature controls, which are the factors that create patterns of hot average temperatures, cold average temperatures. Average is all the months divided by 12. And average or annual temperature range. And temperature range is the difference between the hottest month and the coldest month. So we'll talk about temperature scales and conversions, how to convert back and forth between Fahrenheit and Celsius. The biggest, and this is the real reason that I made this video, this is the most important point right here, temperatures versus degrees. It's something that you've probably never heard of, something that you've never even thought about. A temperature, how hot it is, that's what we talk about. We talk about temperatures. It's 68 degrees Fahrenheit. It's 20 degrees Celsius. Those are temperatures. We're all used to those. What we're not used to is degrees. Degrees are the number of degrees between two temperatures. So it's the difference between two temperatures. For example, 18 Fahrenheit degrees or 10 Celsius degrees. And we'll come back to those. Those numbers are special, and you'll see why in a minute. So temperature, how hot it is, 10 degrees Celsius. This is the way, the syntax for a temperature, the number, the degree symbol, and then the system. 10 degrees Celsius, that is a temperature. 50 degrees Fahrenheit is the equivalent temperature for 10 degrees Celsius. Again, it's the number, the degree symbol, and then the system. That's how you know it's a temperature. Degrees are the number of degrees between two temperatures, or the difference between two temperatures. So from 0 degrees Celsius temperature to 10 degrees Celsius, there are 10 Celsius degrees. So 10, the number, space, system, degree, that tells you that's a degree. Those are 10 Celsius degrees. It's not a temperature, it's 10 Celsius degrees. So degrees are between temperatures. For example, between 40 Fahrenheit and 60 degrees Fahrenheit, there are 20 Fahrenheit degrees. Degrees, again, between temperatures. I'm just going to keep going for a bit. From the melting point of ice to the boiling point of water using the Celsius system, from 0 degrees Celsius to 100 degrees Celsius, there are 100 Celsius degrees. The equivalent in degrees for Fahrenheit, from 32 degrees Fahrenheit, the melting point of ice, to 212 degrees Fahrenheit, there are 180 Fahrenheit degrees. So when you're talking degrees, 100 Celsius degrees, the difference in degrees between melting ice and boiling water, 100 Celsius degrees equal 180 Fahrenheit degrees. If you divide that by 10, you get 10 Celsius degrees equal 18 Fahrenheit degrees. But, and this is a big but, difference between 10 degrees Celsius and 20 degrees Celsius, so that's 10 Celsius degrees equals 18 Fahrenheit degrees. So 10 Celsius degrees equal 18 Fahrenheit degrees. But 10 degrees Celsius equals 50 degrees Fahrenheit. Those are temperatures, 10 Celsius, 50 Fahrenheit. If at this point you just realized, wait a minute, something just happened, congratulations. At this point in my lecture, once upon a time, the entire class completely broke down into angry confusion of the, wait a minute, you're saying that 10 Celsius degrees equal 18 Fahrenheit degrees? And I said, yes, they do. And the whole class said, but wait a minute, now you're saying that 10 degrees Celsius equals 50 degrees Fahrenheit? And I said, yes, it does. Because I thought maybe this semester I can just skip over the difference between degrees and temperatures and the different formulas and how all that works. But no, it didn't work. It just confused the hell out of everyone. So that's pretty much it. 10 Celsius degrees equal 18 Fahrenheit degrees, 10 degrees Celsius. That's a temperature equals 50 degrees Fahrenheit. That's a temperature. So degree Celsius, that's a temperature. Celsius degrees, those are degrees. Easiest way to remember, you already say temperatures correctly. 0 degrees Celsius, that's a temperature. If the last thing is degrees, it's a number of degrees. For example, 100 Celsius degrees, you're talking about a number of degrees, the difference between two temperatures expressed in degrees, because you say it differently. 100 Celsius degrees. Oh, last thing I said was degrees. If the last thing you say is degrees, you need to use the formula to convert degrees, not the formula to convert temperatures. So let's see. 32 Fahrenheit degrees. Oh, that's right. That's a number of degrees. 32 degrees Fahrenheit, that's a temperature. Degree conversions, 100 Fahrenheit degrees equals 100 Celsius degrees, 18 Fahrenheit degrees equals 10 Celsius degrees, 1.8 Fahrenheit degrees equal 1 Celsius degree. So to convert from Celsius degrees to Fahrenheit degrees, you just multiply by 1.8. To go from Fahrenheit to Celsius, you just divide by 1.8. That's pretty much it. Temperature conversions, yeah, there's this 32 degree offset. So we already know 1.8 Fahrenheit degrees equal 1 Celsius degree, but then you got to add in the 30. I don't care how you do this. I've memorized the formula because I've been doing it long enough. You can use a website. I don't care. I want you to get the right number. I don't really care that you know how to use a calculator. That's not what I'm trying to test you on. So Fahrenheit, the temperature, the Fahrenheit temperature minus 32 divided by 1.8. And the reason I'm using these numbers is not only to illustrate that there's that 32 degree offset at 0, but that I like to plug in numbers that I know are going to work to make sure I'm using the right formula. So let's see, 100 degrees Celsius times 1.8 is 180 plus 32 is 212. So that's good. And then we could do it the other way around. 32 Fahrenheit to what's 32 Fahrenheit converted to Celsius? 32 minus 32 is 0. So 32 Fahrenheit, 0 degrees Celsius. Those are temperatures. Temperature, the biggest problem you're going to have is probably remembering which formula to use. Just look for whatever's last. If whatever's last is degrees, then it's degrees. The second problem is forgetting to round correctly. Yeah, I talk about that a whole bunch in the longer videos. Use a website, use a converter. I don't care. Just remember that you're using the right formula and that you're rounding correctly. Just use the right formula and rounding. So, rounding temperatures. The answer has to have the same number of decimal places as the question. So in this case, if I asked you to convert 20 degrees Celsius and I gave you the number as 20 degrees Celsius, the answer, the output has to have the same number of decimal places, integer in, integer out. If I gave you 20.2 and you plug that into the formula, you'd get 68.36. That would be wrong. The question had one decimal place. The answer has to have one decimal place. So you'd have to round up the 0.36 to 0.4. If I gave you 20.22 and said convert this, and you plug it in, you're going to get 68.396. And the correct answer would be 68.40. Since the input had two decimal places, you'd actually need to preserve that 0. However, in Canvas, you can't. If there's an ending 0, Canvas just terminates it, just like Excel and the spreadsheets do. It doesn't preserve that. But when you enter it in Canvas, if the answer has a final 0 to give it the same number of decimal places, Canvas won't accept it. Don't worry about it. It won't get marked wrong. I've put that in the instructions. So the answer needs to have the same number of decimal places unless the final decimal places is 0, in which case don't worry about it. Wind chill. If the wind blows on you, you feel cold. There's a chart. It tells you the temperature in Celsius and Fahrenheit, and then the wind in kilometers and miles per hour. Calm day, if it's 40 degrees, it feels like 40 degrees. If it's 40 degrees out and the wind is blowing at 20 miles an hour, it's going to feel like 30 degrees. That's fun. The other one is the heat index. And the heat index, these numbers are all in Fahrenheit. So if it's 100 degrees with 5% humidity, if you're humble, if it's 100 degrees out and you're humble and it's only 5% relative humidity, it's going to feel like 93. It'll actually feel cooler. Like if you're in Phoenix, Arizona, or Las Vegas, or one of those places where they say it's a dry heat. If it's really dry, it'll actually feel cooler than it is. However, if the relative humidity was 65%, it would feel like 136. So heat index, the higher the humidity, the higher the perceived temperature. And this is probably the second most important. Well, actually, it's the most important. It's not the most difficult. The Celsius degree and temperature conversions, I think, are the most difficult part of this lab. The temperature controls is the most important, but I think it's easier because you're just dealing with ideas and not math. So if you remember it's cool to be high, you'll be set. And when I say it's cool to be high, what I mean is, well, let's look at the principal temperature controls. Talking about average temperature. So you take the daily high, daily low, you average those out over the month, and then you take those 12 months and you average those temperatures, you get the average temperature. It's all months averaged out. Temperature range is the other temperature factor that we're going to talk about, the other element of analyzing temperature with regards to geography. The temperature range is the summer high monthly, or the summer monthly temperature minus the winter monthly. So the summer high average temperature minus the winter low average temperature. The main controls on patterns of temperature, you're going to see latitude, responsible for 95% of everything in this class. If it's not latitude, it's probably been affected by plate tectonics, but latitude is going to affect average temperature and temperature range. Land-water heating differences cause continentality. Water doesn't really change temperature. The land heats up and cools off 4 times as fast as the water. So the land has a much bigger temperature range. The farther inland you are, the more surrounded by land you are, the higher your temperature range is going to be. Ocean currents, I'll talk about that in a minute. Elevation, it's cool to be high. High elevation, it's cold. Also, the daily range increases, but it doesn't really affect the annual range, the increase in elevation. So latitude, it affects average temperature. High latitudes are cool, like the poles are cold. Low latitudes, the equator, it's hot. Latitude also affects temperature range. High latitudes have high ranges. Low latitudes, like the equator, have low ranges. So looking at the equator, or, in the tropics anyway, Salvador in Brazil, 13 degrees south, you can see the average temperature looks like it's maybe 76, 77 degrees, and they have a range of, 4 degrees, 5 degrees over the course of a year. As opposed to Montreal, Quebec, you can see as you get farther away from, this is 13 south, now at 30 north, New Orleans, the average is lower and the range is higher. In Montreal at 45 north, the average is still lower and the range is still higher. Barrow, Alaska, the average is lower and the range looks about the same. So as you get away from the equator, the average temperature gets lower and the range gets higher. Continentality is caused by land-water heating differences. The water heats up and cools slowly. Places by the coast have a small temperature range, daily and seasonal. Inland places have a large temperature range. We call this continentality versus marine climates. The marine climates on the coast have a small temperature range. Here are some reasons. I go over them in the other video. We look at San Francisco with a smaller range as opposed to Wichita. It's not only hotter, it's colder, well below freezing, as opposed to San Francisco getting down to an average low of 50 to 65. So they've got like a 15 degree range. And here we're going from 30 to 50 degree, 15, 30. And that would be 30 Fahrenheit degree range. That would be a 15 Fahrenheit degree range as a function of continentality. They're about the same latitude, but their range is much more extreme because of continentality. Ocean currents and sea surface temperatures. All over the world on the East Coast, there are warm currents, and all over the world on the West Coast, there are cold currents. Warm currents evaporate more easily, so you get more rain if you're by a warm current. The air temperature is higher. There's more humidity. You get more rain. We have the opposite, right? We've got a cold current offshore, so we don't get as much rain. As opposed to places on the East Coast, the Southeast, they get lots of moisture for summer rain coming off of the Gulf of Mexico, which can hit 90 degrees in the summer. So in the Northern Hemisphere, because of the patterns of air circulation, the oceans rotate clockwise in the Northern Hemisphere. So you can see here's the Japan current coming down, the Kuroshio current coming down, becoming the California current. Over here, it's the Japan current, warm water moving towards the poles, cold water coming down from the poles, the cold California current. Same thing here in South America. You've got cold water coming up off of the Antarctic and warm water coming down. Everything in the Southern Hemisphere spins counterclockwise. So there's cold water on the West Coast and warm water on the East Coast. Cold water on the West Coast, warm water on the East Coast. Elevation, it's cool to be high. High elevations are cool. If we look at this global map, and I'm about to show you a whole bunch of different maps of average temperature and temperature range. So you can see the main trend is latitude. The tropics are hot, the poles are cold, followed by, so it's latitude and elevation. You can see like the Ethiopian highlands, the Tibetan plateau. Like it's really cold there. It's warm at the same latitude. If it's colder at the same latitude, it's probably a result of elevation. The Alps, the Rockies, the Sierra Nevada. You can see the Andes standing out very clearly. In fact, those are the only places that are really hot in the tropics in South America, are at really high elevations. So this is average temperature, latitude followed by elevation. Now I've got temperature range. It's latitude again, with the tropics having the lowest range. As you move away, for example, across the plain states, the range increases because of latitude. And as you move inland, there's kind of these concentric rings, especially over Eurasia, with the highest temperature range at a high latitude that is well inland. This is one of the reasons that there's high continentality in the Northern Hemisphere, low continentality in the Southern Hemisphere. There's just no data for Antarctica. It's not that they have no range, it's just no data. But there's no landmass. Like here we've got the Tropic of Cancer and Capricorn. So this is 30 degrees south. So Sacramento, the same latitude of Sacramento, there's nothing. You're just in the ocean in the Southern Hemisphere. So there's no big landmass at a high latitude in the Southern Hemisphere. Here we've got average temp. Again, it's the effect of latitude and elevation, high elevation, cold temperatures. Average temperatures across the U.S., you can see the effect of the Appalachian Mountains. You can see the Rockies. You can see the Sierra Nevada. You can see the transverse range down here in Southern California. You can see the effect of the Mexican Cordillera, the range of mountains there. You can kind of see, I can see on my monitor, I don't know if you can, the Cascadian volcanoes, like right there. It's probably Helens or Rainier, probably Rainier. Temperature range again, it's latitude and continentality. Temperature range in the United States, you can see the lakes don't change temperature a whole lot. They don't heat up a lot, they freeze, but it's mainly latitude and continentality. The farther inland you go, the higher the range is. So as you move inland from the coast, the range gets higher and higher and higher and higher. Elevation, I made some new maps in a funky color scheme so that you could see, the yellow places are all over 12,000 feet in elevation. So you can see the Sierras, you can see the Rockies, you can see the Appalachians standing out against the lower elevations. Temperature range, yeah, you can see again, here's the Appalachians, here's the Rockies, the Sierra Nevada, the transverse range. There's the transverse range, the Sierras, the Rockies, the Appalachians. Creating patterns of average temperature, latitude, and then elevation, elevation, elevation. That's it for the Lab 4 intro video. I wish you good luck on this week's lab. If you have any questions, please come to Zoom. This is an excellent example of one of those labs that if you're just not getting it, 5 minutes of conversation can change it, and the lab, instead of becoming horrible and difficult, is going to become busy work. hopefully not too much busy work. Hopefully just enough that you actually feel confident doing the problems, that you feel confident in your abilities to successfully do the lab. That's the amount of work that I'm going for in all of the labs, is just enough work that you feel confident that you understand it. I'm never going for busy work. I think if I give too little work, then you don't know if you can do it. Like, you did the lab and it was easy and it was quick and there wasn't a whole lot of work, but I'm not sure if I know it. So I'm always trying to give you just enough work so that you feel confident that you understand it. You feel confident that you're succeeding.